Hi, it's me, Paula, the math tutor, and in this video we're going to be calculating probabilities of normally distributed random variables without using technology. For that, first we are going to see how the mean and the standard deviation affect the normal curve and how we can use them to estimate the area under the normal curve. And then we're going to try an example. So let's begin. In the previous video, we introduced the normal distribution and we saw how the graph of this density function looks like. We know that it has this ball shape and it's defined, the position of it and the general shape actually, it's defined by the mean and the standard deviation. Those are the only two things that are going to define a normal distribution. All normally distributed variables have the general same density function. It's just affected by the mean and the standard deviation. Those are the two things you need to define it. Because all of them have the same shape, the areas of all of them are going to come from what the mean and the standard deviation is, but we are going to have some standard values for each of the parts of your area. So let's see the graph again. This is the graph of my normal distribution with a certain mean, a certain standard deviation that I can modify from here. We know that because this is the density function of a random variable that is normally distributed, most of the values that x can take are going to be close to that mean. So if my mean is here, most of the values are going to be close to it. Actually, most of the values that x can take are going to be one standard deviation or less from the mean. So if my mean is mu, I'm going to be between mu plus sigma and mu minus sigma most of my values I'm going to have. But I then could move a little bit further. I could move 2 standard deviations from the mean, or 3 standard deviations, or even more. And the likelihood of x getting those values gets less and less likely. We know that this is a continuous random variable, which means that the probability of x being between 2 values is going to come from the area under the curve. And as all normally distributed variables have the same curve as their density function, the areas are actually pretty much the same, depending on how many standard deviations you move from the mean. Let me show you what I mean with this. If I calculate the area between mu minus sigma and mu plus sigma, here I'm gonna have 68% or 0.68 as an area, so 68% of probability of x being between here. Then between mu minus 2 sigma and mu plus 2 sigma, the probability of x being there, or the area under this curve, is around 0.95. And the area between mu minus 3 sigma and mu plus 3 sigma is 0.997. So 99.7% of probability of your x being between these two values. Here I have the actual areas, and you can see that between mu minus sigma and mu plus sigma, I have 0.68, so 0.34 and 0.34. Between mu minus 2 sigma and mu minus sigma, I have 0.13, so around 13%. And on the other side, same thing, because this is a symmetrical curve, so everything that happens to the left of mu happens to the right. Then between mu minus 3 sigma and mu minus 2 sigma, or between mu plus 2 sigma and mu plus 3 sigma, I have 0.02, so 2% of probability of being in this area, and of it being between mu and minus 3 sigma and mu minus 4 sigma, or to the other side, is 0.0050. And look at this, you can change the mean, or you can change the standard deviation, and these values are actually the same, they're constant. For any normally distributed continuous random variable, this is going to be true. So if you remember these values, and I highly suggest that you learn them, you can calculate a lot of probabilities, a lot of situations that involve normal variables just by knowing this data. So if you have a normally distributed random variable and you know the mean and you know the standard deviation, you can calculate a lot of probabilities if you are in values that are at a certain standard deviation from the mean. So if you are 1 standard, 2 standard, 3 standard deviations from the mean, you can actually calculate the probability of your variable being between values because you know these results and you can use them without the calculator because you know that this is going to work for any normal distribution just by knowing the mean and the standard deviation. Let's try an example so we can see what I mean with this. Let's say the height of female students at a university is normally distributed with mean 170 centimeters and a standard deviation of 8 centimeters. A parenthesis here, heights are actually something that it's very easy to simulate with normal distributions, and you'll see a lot of examples like this where they measure heights or they measure weights or things like that, and they use normal distribution to know probabilities. What is the percentage of female students whose height is between 172 and 170? Okay, so first we would need to draw our normal distribution. So if I draw this normal distribution, I'm going to have my bell curve centered in 170, and I know my standard deviation is 8. So if I move 1 standard deviation to the left, I'm in 162, and if I move 1 to the right, I'm in 178. They asked me for the probability of x being between 162 and 170, so I'm in that first area. And I know that the probability of that, the area under the curve between those two values, is 0.3413 approximately. And that solves question A. Let's say they ask us for the probability of x being between 170 and 186 centimeters. In this case now I have to stack two of these parts because 186 is 2 standard deviations from the mean. I know that from the mean to 1 standard deviation is 0.3413, and then from 1 standard deviation to 2 standard deviations, the area under the curve is 0.1359. So if I add those two, I end up with 0.4772, around that. Meaning that the probability of randomly picking a student that is between 170 and 186 centimeters in height is 47%, something like that. Now, what is the probability that a randomly chosen female student has a height less than 154 centimeters? 154 centimeters, if you notice, is 2 standard deviations to the left of the mean. So we are going to be calculating the probability of x being less than or equal to 154. An easy way of doing this is remember that the whole area between negative infinity and infinity of the normal curve is 1, because it's a density function, so it needs to be 1. If I want the probability of x being less than 154, what I can do is I can do 1 plus the probability of x being larger than or equal to 154. Remember that the equal here doesn't do anything, so you can write less, more, less than or equal to, more than or equal to, it's the same. But because I'm calculating now 1 minus the probability of x being larger than, now I can divide this in 3 parts. First, the part that is between 154 and 162. 2 standard deviations, 1 standard deviation to the left of the mean, and that is 0.1359. Then the area between 1 standard deviation and the mean, because it's 162 and 170, and that is 0.3413, and then from the mean to infinity, the area is 0.5, it's 1/2, because the mean is in the middle, and I know that the total area is 1, and I know that this is symmetrical, so I'm exactly at 0.5 here. So now what I can do is 1 minus those 3 areas, and the result of that is 0.0228 approximately. So around 2% of the students are shorter than 154, so if we randomly pick one, we can expect that to be the probability. And this is it for this video. In the next one, we are going to be calculating normal probabilities, but with technology. Because in this video, we depended on the values we had to be some standard deviations away from the mean. What if we want to calculate it, but for any value, not necessarily something related to the standard deviation? For that, we're going to use technology, and that comes on the next video. Bye bye!